All right, so thanks for the introduction. I'm Faiz Ahmed. I'm in mechanical engineering. My group primarily works at the intersection of, let's click here, of AI and engineering design. So I wanted to give you kind of like a very quick overview of some of the things that we think about, but most importantly, enable you to think on what are the different connections of AI with the physical world. And in this case, let's first start with when I said we work on AI and engineering design, what is design? And if you look around yourself, you will see that you're surrounded by design, whether you took a flight to come to Boston, whether you're driving, whether you are biking here, if you go and use energy, you have energy solutions, you have wind turbines, batteries, all these products are created by someone who came up with a design that this is what it should look like, this is how it should function, and all the systems that go into place, right? And a key question is, how are they designed and what role AI plays in it? So let's just take the example of one of these products. And I'll take cars, for example. I asked a friend of mine, Bill, and asked, like, how do you actually create cars in the industry? And the first answer was like pretty much what we study in our design classes, the design process. You start with some market research, do early stage design sketches, then start modeling, simulation, go to the wind tunnel and test those products and iterate and finalize. But if you kind of dig a bit deeper, Bill will tell you that the process is much more complex, and anyone who has done any serious design will relate to this, is there's lots and lots and lots of back and forth. And in fact, like in the car industry, they call this the devil's cycle. There's a good reason for that, because going from a concept to the product can take many years, 3 to 5 years in this case. And more importantly, because exploration is so expensive, every time you come up with a new sketch, like you have to really explore the design space. People don't do that much. So they would tweak the design a little bit and use the ones that were there before. And this leads to innovation loss, difficulty meeting requirements. And there is research showing that 70% of the life cycle costs of a product are decided by decisions taken in early stages of design. So there is, and this is not just about car industry, right? Like any products we are deciding, there is the early stages decisions we are taking has a huge cost implication, and exploration is expensive, right? All right, so then since we are working on AI, our natural question is how can AI enable humans to create better designs faster? And this touches on a lot of sectors, from aerospace, automotive, energy, shipping. And some people would ask me, what is better? And this is critical because, in fact, you define better, right? For someone, it might be cheaper. For someone, it might be more sustainable. It might be faster. So it might be like other values, like maybe more better looking product and so on. So now let's talk about generative AI. How many of you have already had some experience with generative AI? Awesome. Great. So when I think about generative AI, I always like to show people this one-dimensional histogram. Effectively, what most generative models are doing is they have some samples that they have seen. In this case, it's just values between -25 to 15. And they can learn a parametric model to predict the distribution, and then you can sample from that distribution. Right. Fundamentally, this is what most models, whether we are talking about diffusion models, language models or so, are doing. And the more important thing is that these models are not new. These have been around, generative models have been around for decades, mixture of Gaussians, topic models, and so on. But what's new is that now we can learn much, much, much more complex distributions. This is like I teach an AI for design class, and you can see the best text to image generator out there in 2021 versus 2022, 2023, 2024, and now we have video generators, right? So what we have seen is with a lot of compute, a lot of data, and a lot of good algorithms, there has been this dramatic change in quality that we are observing. And a natural question that my group thinks about is, what happens with the physical products? What happens with engineering, right? Engineering is difficult because of lots of factors listed here, but primarily there is a lack of data. We are not blessed with trillions of tokens, so we can't train foundation models easily. There are other challenges like understanding engineering performance, like what physics is at play, what are the design space parameters. Humans don't think in a unimodal way. If you're designing a product, you're speaking, you're looking at visuals, and you're thinking in different aspects, so multimodality and so on. So with that, I want to kind of go through some examples of things that were, despite all the hype, like where we see promise and where we see that work needs to be done for next generation of AI to be capable for shape, design, and manufacturing. And I divide it into two parts. One part is AI helping humans solve problems that humans are already doing and pretty much not using a lot of AI today. Second part is AI helping humans or people solving simulations where current models are good enough, but you can do actually much better. And third is where actually the current models can't even solve the problems. So we can solve problems that were not possible before. So the first case is bicycle design. We collaborated with a company called BikeCAD. These are globally, a lot of frame builders go on this CAD software and design their bicycles. And when we started looking at designs, we found that we wanted to enable AI to create designs for people, but it was not trivial because people have very, very diverse set of requirements. So in this case, you might say, I want a bike which is lighter and more ergonomic, but is also black cyberpunk style road racing bicycle. And here we are not generating images. These are CAD models, these are renderings of CAD models. So now, should I change the saddle height of my bicycle or should I change the color to actually meet these requirements, but also all the physics requirements? You want it to be like more stiff, you might want it to be more aerodynamic. So we're running simulations and so on. So we started looking at it from a combining learning and optimization perspective, and multimodal learning plays a big role. The other thing we started looking at is, can generative models be an AI design assistant? And when we started talking to people, sometimes designers are lazy. So they go to the CAD softwares and they design a part of the CAD model. So they might design the frame and say, just complete it, auto-complete it, right? So what we did was we trained models on past data. And these are diffusion models. These work on Excel sheets where you imagine that some columns of Excel sheets are missing, and the diffusion models can fill in those values. And they are also guided by the structure of the bicycle. So with that, you can effectively see that you can give incomplete bicycle designs, and this can complete 3D CAD models of these different types of frames and exact measurements that go on and so on. And once we have all that exact parametric value, you can generate images out of those. All right, other use cases, like thinking about how can AI help humans design, like people design sketches in our classes. And we have shown some prototypes where you can actually go from a sketch to a prototype, like a physical prototype, by going from sketch images, 3D models, and then correcting for some manufacturing defects and so on. This is still early stage because I don't think the spatial understanding is there yet, but we already see some encouraging results. The next thing, if anyone has done design, I think one thing when we think of AI as a designer is it should be able to design and follow the real world rules. How many of you have done a design where you had like a thick rule book where you had to go rule number 1.3.5 and so on, right? So most technical documentation, whether we look at aerospace, whether we look at automotive, medical devices, shipping, trains, they have hundreds and hundreds of thick documents, and all those rules need to be followed when designing products. So we asked ourselves, if AI is ever going to be good at this, it has to understand the engineering rules. Given a PDF of a rule book, it should understand that. And we found that there was no benchmark for this. So we ended up like creating our own benchmark. We collaborated with MIT's motorsports team. There is the Formula SAE book, which is like hundreds and hundreds of pages. It has both visual information and text information. You have to really understand all the engineering drawings in this. And we went out and compared all these common models. Like now we have expanded it, GPT-4, Claude, Gemini, Lava models, and so on. And you can see in most cases, the red line is random. So if the model is randomly guessing the answer, and models are pretty bad at right now. So the models, although there is some improvement for some cases, in most cases, the models actually don't understand the engineering rules. And this benchmark we are using to kind of measure when there is success in the LLM world is actually having success in the engineering world, because we have a standardized benchmark to measure this. Great. With that, there are other set of problems now going from helping humans to solving engineering problems. In this case, I start with structural topology optimization, where we want to find good structures that are stiff, given some loading conditions. And what we have shown is that if we can use data-driven methods, collect a lot of data, amortize the cost of optimization. Basically, you can collect a lot of data, which is expensive early on, but now you don't have to do optimization from scratch over and over again. So every time you run an optimization, it forgets about everything that has happened before. So you can use that, and in this case, we found huge speedups, 2,000 times speed up, while being reasonably accurate at 99.6% accurate. Anyone who has done Bayesian optimization is something that is used a lot in experimental design and so on. There also, we saw that some tabular foundation models can lead to huge speedups. In this case, this is a car crash problem. Gaussian process-based Bayesian optimization takes 2 hours, and we can solve it in 3 minutes at a better optimal solution. So this is just showing that these models are not just there to give you answers, but they can support things, very fundamental things like Bayesian optimization and topology optimization and so on. The third problem, which I personally like a lot, is around linkage systems. And in this case, there is the way these linkage systems are. If you're designing a robot or your car wiper door, this is my student trying to design a linkage system. You draw a curve and you ask a mechanical system driven by a single motor to actually trace that curve, right? This problem is extremely challenging. And the reason I know it is if we have looked at industrial solutions and they can't solve this problem. But also, for the last 3 years, I've been running this contest in my class where I would ask the students to draw some characters. In this case, this is the latest. This year, students had to come up with a linkage mechanism which can draw these curves. And the winner, after 2 weeks of work, is this, which gets pretty close, but it's still not capturing very fine features. And this is 87 MIT students working for 2 weeks trying to solve this problem using optimization methods. So it's a fairly hard problem. The way we approached it from a research perspective, we created our own simulator 800 times faster than what existed before. We created a data set with 100 million mechanisms. And with that data set, and so again, I'm not going to the details, like the idea is to use contrastive learning and to learn joint representations in space. We can effectively show that the problem can be solved much, much more accurately, 57 times more accurate, while being 165 times faster. So instead of taking 45 minutes, now you take 15 seconds. So you draw a curve and you get a physical mechanism, and you can actually manufacture that. And you can guess who funded the work. In this case, we can write much more complex things and say, give me a mechanism, and within 15 seconds, you can get a solution. All right. So, and you can also incorporate manufacturing constraints, like there is lots of nice cool things where you have to make sure that this 3D mechanism doesn't collide with each other and always has like no defects. But again, the idea is like maybe you don't care about linkage mechanisms. This is a problem which has mixed representation. It has a discrete structure and it has continuous values, right? And a lot of engineering and systems engineering problems have that. And again, going from compliant mechanisms, molecule design to network system design, most of these systems, if they are represented, the methods are actually quite broad. And in fact, we are using it in a DARPA project right now for designing turbine bliss. We have been looking at other applications that they apply to. And with that, I want to wrap up with this key idea that what is kind of holding us back? What are the key challenges if you're working on engineering systems? And the biggest bottleneck right now is that modern AI is sitting at 10 billion to 10 trillion data set sizes or tokens, however you measure it. While engineering design, if you're lucky, if you get 100,000 or 10,000, you start feeling very lucky. 100,000, you're really happy, right? So we have to bridge this gap by either creating more data sets, which we have done. We created this data set last year, which is one of the largest in the automotive industry, and it's being used by many, many companies already, where you have high fidelity simulations using 3 million CPU hours to actually simulate cars and the entire 3D flow fields and so on. But also, like, I think this is a community effort, and you have to think of how much data is there and what data you can leverage. Can you actually leverage synthetic data, which is a very promising approach. So with that, for thinking about next generation of AI for design and manufacturing, there's a lot of things to think about, how we can create better designs, how we can tap into worker knowledge, how we can scale up compute for some of these challenges, and enable design democratization. What is design democratization? Like, I asked generative models like ChatGPT to write a poem about kinematic designs, and it writes this poem. Robotic arms with joints so fine move with grace in a straight line. Machine learning is the key, it seems, to design them with great esteem. Great quality of poem given my standards of poem writing. Similarly, my daughter made like a doodle, and I asked with her permission to give it to models, and it actually makes pretty good approximations. And again, some of it is hallucination, but hallucination is both a feature, right? It's a feature here because it's actually coming up with things that she may have imagined. And I see this as art democratization. People who are not necessarily trained as poets and artists can actually enhance the quality of their work and get help from AI. So the question is, how can we get to a stage where we can have serious generative AI models help novices and experts in understanding design requirements, preferences, simulating, prototyping physical products, and producing manufacturable designs. And not just for car designs, but this applies to a lot of products that are out there where the design cycle can be significantly accelerated or create better products. With that, I'm happy to take questions. Feel free to reach out to me if you have any questions. Thank you.
How do you think about applying this in like actual factories where a lot of what you explained feels like the hammer? Where do you find the nails where you can actually go implement it?
Yeah, so I think eventually the nails come from domain experts who are working there, and it comes through a lot of collaborations. So some of these methods are actually created for engineering specific problems. So these are not problems where you download a code and run it, because those methods don't often capture some of the engineering performance and the physics and so on. And then you need the person on the floor to actually understand some of it or collaborate with someone to bring in significant changes. I worked in the industry back in Australia in the mining industry, and I think one of the biggest things that I saw was that the bottlenecks are not tech. Many times the bottlenecks are just the inertia, right? And people wanting to change or not. So I agree. I mean, this is a huge thing.